We are very happy today to have Professor Harald Kunstmann. He is a professor in Germany at Augsburg University. He earned his doctorate at Zurich in Switzerland in ETH in Switzerland after studying physics in Marburg, Germany, Virginia in the US, and Heidelberg in Germany. He conducted research at the University of Bloemfontein in South Africa and the University of Oxford in the UK. He is the Deputy Director of the Campus Alpine at the Karlsruhe Institute of Technology in Germany, and he has held the chair of Regional Climate and Hydrology at the University of Augsburg since 2009. Since 2021, he has been the founding director of the new Center for Climate Resilience there at the University of Augsburg. His field of research is the impact of climate change on the water cycle. He works not only in regions of Germany and Europe, but also in the global south, particularly in various regions of Africa. He is leading international projects on hydrology and climate-smart agriculture and on improved seasonal forecasts in Africa. In 2021, he was awarded the Water Resources Prize of the Ruhiger Coast Border Foundation. He received the German Hydrology Prize from the German Hydrological Society. Harald, we are very happy to have you on board with us. The floor is yours. You are welcome to kick off with your presentation. Thank you.
Okay, thank you very much for this very nice introduction. So you see my presentation in presentation mode, right? Okay.
Yes.
Okay. Yeah, thank you very much for your kind invitation. And of course, it's a pleasure. I feel very honored. And yes, yeah, I come from natural sciences, but it's very nice to be in so close contact in the field of water with you from economic sciences and from politics. So, but of course, my background is natural science, and of that is also what, let's say, the most part of my presentation is about. And today it's on seasonal predictions, which means how far can we really predict wet, cold, dry anomalies in the future, in the coming months. And that, of course, has high societal but also economic relevance, because it would allow planning and anticipatory action. And that is why Djiby and me said, okay, that could be interesting for your series. For me, it's really always nice to be in contact with groups and people from South Africa. As Djiby mentioned, in the mid-late 90s, I was for several months as a still PhD student in South Africa at the University of Bloemfontein. So working more in the field of groundwater in those days. So you see myself with, let's say, mid-late 20s. This you may know because that is the waterfront in Cape Town. Yeah, and of course I walked in the Karoo area and in the field of groundwater. But I also worked as part of my PhD on sustainable water management of a specific aquifer in Botswana, the so-called Road aquifer. But I need to say, actually, my PhD was more on the development of methods, stochastic methods, and then I applied these methods to different questions worldwide, and the Road aquifer, Botswana, was one of it. And I enjoyed that very much. So even you may not expect this title here, it was really on a very methodological, computation efficient approach to estimate groundwater recharge. That was also published in Water Resources Research, and you see here Road aquifer in the middle of nowhere. And in parallel with that, I worked also on sustainable pumping rates together with the Bloemfontein colleagues. It was on sustainable yields of boreholes and how to do that with, let's say, with pumping test analysis. And the Karoo is very demanding because it's fractured media, and the typical porous media approaches do not really work. And being a physicist, I was able to contribute a lot here, and I remember these times as very nice and valuable times in my life. In the meantime, yes, years ago, I was happy to work again in at least have a research project in South Africa. That was now more in field of atmospheric science, hydrology. Here we worked on soil interactions to precipitation, and we were also aware of, let's say, dependent on the soil data, in particular also here in Southern Africa, you take and how you describe this, the main soil types and properties, that it can have severe impacts on derived, modeled land surface atmosphere interactions. Yeah, so very nice to be now, at least digitally again, in contact with you in this very special part of the globe. But let's come really to the topic, and I would like to invite you to have a look on Europe. I bet you are well aware of your challenges in South Africa too. But it's also, let's say from my side, even in Europe, I mean, we really have to deal now a lot with droughts and with heats. Just looking back to the last summer, the summer 25, yeah, that was an exceptional heat wave in parts of Western Europe. And you see anomalies here of tremendous magnitude, and it's not only on the land surface, it's also when we look at the sea surface anomalies. I mean, in the Mediterranean region here, June, where many Europeans like to go for summer vacation, I mean, we have sea surface temperatures anomalies up to 4 or 5 degrees centigrade. That is really tremendous. Yes, and that is, of course, economically relevant in all regions. We have that here. That is an example from Bavaria. I will talk about that later. In Italy, the Po River, main river system in northern Italy, was completely dry, and also in your continent, in the Greater Horn. Are you seeing the slides?
Yes.
I'm now with slide number 6. Yeah.
I'm not seeing the progress of the slides. I'm seeing the slide number 1.
Okay, then it is not. But I'm on slide number 6 now.
Okay, let me perhaps.
Yeah, from my side, I can see them. Thank you.
Okay.
Okay.
Okay, then that's fine. Then perhaps. Okay, I also see another time. Then that's fine. You can proceed, Harald. That's
okay.
Good.
Okay. Yes. So I'm on slide number 6 now, and I will talk about also of this very challenging region of the Greater Horn of Africa. Yeah. Now, so, and if we know better in advance, if there are drought or heat spells is coming, that would, of course, allow proactive management and action. And that is why I think this work is societal relevant. When we talk about seasonal or sub-seasonal to seasonal predictions, what do we mean? We abbreviate that with S2S, sub-seasonal to seasonal. And of course, you are well aware of weather forecasts. Yeah, they forecast hours, days, maybe up to 2 weeks. For many years now, for decades now, we look forward 50, 100 years in advance with our climate projections. Yeah, but that is scenarios. Yeah, giving specific greenhouse gas emissions assumptions. What would that mean for our climate, which means long-term averaged weather, so to say? But this is now in between, let's say, starting from some weeks till some months. Yeah, how far can we predict these kind of, let's say, anomalies? And that, of course, is of high importance for agriculture, because it would allow planning of what to seed. Yeah, but of course, in terms of water management, clearly, if we know a drought is coming, we would manage a big reservoir like here, the grow Ethiopian rhino stem differently from case we know we approach a normal season or a wet season. So that is up to 215 days. 215 days comes, that is 7 months. That comes to the fact that in our work, we are very much focusing on specific data coming from the European Center of Medium Range Weather Forecasts. And they are publicly available for research purposes. We also have, let's say, a more direct access, also in more higher spatial resolution. But you would say, okay, I mean, these seasonal forecasts, they are available. So what's the matter? What are you doing here, Mr. Kunstmann? Yeah, just go to the site and have a look and then download the results and then everything is fine. Yeah, I will tell you why this is not that straightforward, just downloading this data. And what is it actually about? What is ECNWF and what is this community? What are the big international services are doing when they do sub-seasonal and seasonal forecasts? Now, in ECNWF, they run coupled atmosphere, ocean, land, sea ice model. And they do it in 2 ways, in a sub-seasonal mode and in a seasonal mode. In the seasonal mode, the forecast is up to 7 months. It has 36 kilometer horizontal resolution, which means the initial condition is perturbed 51 times, and then you let the model run 215 days, which is 7 months into the future. And so we have 51 ensemble members, and that also allows us to draw, to get information about probabilities. Yeah. There's also sub-seasonal forecast. They go up to 46 days. They have a 6-hourly temporal resolution, and this is even up to 100 members. Today, I'm talking only about the seasonal ones. So that is what it looks like. Yeah, a very fancy, complex model system which is applied here. Yeah, particularly important is that also an ocean model is included, because the ocean temperatures, they determine a lot via remote teleconnections, yeah, weather and anomalies far away. I mean, El Nino now is approaching, and you're well aware that El Nino has an impact far, far away from the Pacific coast of Peru. But when we use the direct results here, what is the problem? The raw C5 forecasts here, unfortunately, the skill is very, very low. We say they have issues, so to say. Yeah, that is now the percentage deviation from the precipitation forecast for lead month 1. Lead month 1 actually is the second forecast month. Lead month 0 is month number 1. Lead month 2 is already up to 2 months. And we see worldwide, including also the southern African part of the globe, we have deviations in precipitation amounts which are tremendous. Yeah, more than 60, 80%. Yeah, and that means even when you do a poor man climatological forecast, would say, okay, the coming months, the forecast for the coming months is the climatological months. Yeah. That would be the poor man's forecast. And these raw forecasts, they have a performance which is in many cases worse than the simple climatological forecast. Where does that come from? That is an example showing our own little town of Garmisch-Partenkirchen. I select 1 pixel, yeah, and that is now just an example. This is a forecast started in 81. That is when the data set started. And it is the forecast, it's the days since January 1st. Yeah, so it's up to 4 months in advance. So it's forecast for February, March, April, and so on. And that is the delta in the forecasted temperature. And then you see you have ensemble members, yeah, but then you have a bias, which means specific months, they have either a clear over or underestimation of the temperature. Yeah, and that should not be. I mean, this is a clear directed error. That is what we call a bias. So we have biases, but that is not only the only thing. It also, they have a drift. Drift means that your forecast depends on the lead time. I mean, which means if I forecast on April from January or from February, that makes a difference. And there's a clear, let's say, also again a bias, a drift, depending on the forecast period. So you see, the longer we forecast April, yeah, the longer we do the forecast, the worse the directed deviation from the value gets. And that, of course, is a problem. Yeah, and that is what these raw data show. So we need a correction for drift and biases. That is where we are in. And we have developed two different types of corrections. One is a statistical approach. We call it bias correction statistical downscaling. And the other one is a AI-based, deep learning-based method. Our statistical framework, it actually works via quantile mapping, which means we compare, let's say, the observed reference observation to the forecasted, to the raw forecasts, and by trying to get the cumulative density functions closer to each other, that is what we are doing for correction. And that is along with a spatial disaggregation, which means if the reference data has a higher resolution than the raw CS5, then we can even get, let's say, a higher spatial resolution forecast. And in parallel, we also work with AI methods. Here, it's a very specific one. It's adapted Fourier neural operator based methods. We have developed a Python-based tool. It's called PyCast S2S, and this is open source code, and you can have access to it. And that is publicly available and very transparent what we are doing here. How does it work? When we talk about forecast, it's also important to do it in a timely manner. Yeah, it would not make sense that our method takes weeks, yeah, till it can be applied, because it needs to be applied very quickly. So the raw data from ECMWF, they are released around every 5th of each month. Then we need some time for downloading it, and then we need some time for correcting it. And usually 2 days later, not more, our bias corrected results are available. And that also means all our techniques need to be done in a computationally efficient manner. We have different projects worldwide in the last 10 years where we use that. We have a global one, which is called Outlast. We look in the entire globe. We had a long-term project here together with Iran, also with Brazil, also a focus here on the Greater Horn of Africa region, Germany, but currently also in Southern Africa. But I need to say, our approach is we develop methods. Yeah, we are not the experts like you for Southern Africa, not always, but we would like that our methods, we apply our methods for different parts of the world and want to see what is the performance. And that is a very nice co-design cooperation, yeah, to apply methods for different parts of the world and to work together with the local experts. For Germany, I start with some examples. It's because it's very interesting, because in Germany that we deal with droughts is not that old. It's not that old. And when I'm looking back here, this project where we work together with Iran, that started around 2016, 17. And then in 2018, we had the first big drought in Germany. And then it was continued by further droughts. And then it was somehow funny. I mean, it's not funny, yeah, but a bit funny that methods we developed for very dry regions in the world. And we now need it we wanted to see how well do they perform for Germany. Yeah. So what we have learned from other parts in the world, now we felt the need to look how well our methods perform in our own country. And that is what we published here. That is not a very, let's say, prestigious journal. Here it's a small journal, but this journal is read by water managers in Germany. Yeah, they don't read scientific journals. This is still Web of Science index, but it is not, has not a very high impact factor. But it is read by decision makers in Germany in the field of water, and that is why we placed it here. Yeah, and as I said, from 2018 on the latest, but also particularly here, 22, we had a lot of dry years. Yeah, and people were somehow saying, "Ooh, droughts in Germany, what happened?" Yeah, we thought that only happens in other parts of the world, Africa, now Germany. Yeah. Yeah, but what did the forecast actually say? That is now, you don't need to know the details. This is a very specific region in Germany, in the upper part of Bavaria, original region where I'm coming from. And that region is not that wet. It's called Franconia, it's now in Bavaria. And now August 22, that is, was again a very dry August. And the question was, and that is what we try to communicate to decision makers, when we forecast the August from different months ahead. So that is the August forecasted in February. That is the August forecasted for March, April, May, June, July, and then the beginning of August. And then we say, okay, is the forecast more wet, normal, or dry? That is the terciles, yeah. And this number, and the color behind is how many ensemble members fell into this forecast category, which means the darker this yellow, orange, brown is, the more ensemble members fell into this forecast category. And you can already see that from January on, there was the forecast said that August, with more than 50% of the ensemble members of the forecast said January in that region of Germany can be very dry. That was released a little bit then in March, but the latest again here in June and then beginning of July, it was, and that is already 2 months, up 2 to 3 months ahead. It was clear the August will become comparatively dry. So that is already something for Germany, being, let's say, in the west wind drift of the Atlantic Ocean. I thought never ever we will be able to do this kind of forecast, but that was a master study by Jan Weber, and he showed us, even in Germany, we can do something. When we compare then how far was that captured, and even when it appears very little here, we see behind, you see stations from the German Weather Service, Deutsche Wetterdienst, DWD, and in most part of the, when the color agrees, then the forecast was good. But you see for many parts of Germany that the forecast, the color in the circle is similar to the color behind. Not always in southern part of Germany here, yeah, but in many regions you see the forecast was actually agreeing with the observation. Now, precipitation is difficult. Temperature is much easier. Now, when it comes to temperature, to forecast that the summer 22 was completely hot, very hot, even, I mean, from February on, it was clear it will be hot. It will be in the upper 33% hottest August that we had. So temperature is much easier than precipitation. So, and here, precipitation worked rather astonishingly well, but temperature worked even better. But now you will say, okay, Mr. Kunstmann, this is just one lucky guess. Yeah, even a blind squirrel finds a nut once in a while. That is what we say in Germany. Yeah, this does not convince me at all. Now, of course, that is justified. But for that, we need a measure. We need a performance measure, an indicator. And I started easy, and now it gets a little bit more complex. Because when we really want to see the performance, then we need to do a bit of statistics. And we evaluate this kind of ensemble forecasts with what we call continuous ranked probability skill score. What does it actually mean? It means, let's say, if I look at the, I have a specific month, and then I have a specific precipitation value. That is more the Heaviside function in this rectangular Heaviside function. Now, since we have an ensemble forecast, we have a CDF, how well about this forecasted precipitation value. And now, of course, we have our bias corrected CS5 CDF, which is the blue one, but we can also look at climatology, and then we have the gray one. And you may quickly understand, of course, the less the area between this Heaviside function and our CDF, the better the forecast is. Ideally, it would be the same as the Heaviside, but that, of course, is not feasible. But you see, that is how we calculate that. And just to set the scene, we should not, the value can be maximum 1. This is the skill score. The skill score relates here to the climatology. A skill score of 1 means every day is perfectly hit and there is no spread. That, of course, we cannot expect. Yeah? Even when the skill score is 0.7, it still means every day is perfectly hit in the mean and the spread is conserved. This is also difficult to expect. Just to say, a skill score of 0.3 is realistic and already a rather good forecast. It's far better than the climatology. If the skill score is 0, the skill is very equal to the climatology. I would say that is the minimum we should expect. But as I said, CS5 is not fulfilling that in the for the raw data. And then the skill score goes to minus infinity. And that, of course, is then worse than climatology. So if we have values of 0.3, I need to say we are already quite happy. What does that now mean? Case study for Germany. This is now the lead months 1, lead months 2, because we start calculating from 0. This is the raw data, and that is the corrected one. And you see, I mean, when it comes to temperature or precipitation from months 2 on, we already have negative skill scores, which means climatology is better than the forecast. Now, when we go to our correction, we see, for temperature, we are now already in the positive range. We are not approaching 0.3 like we do in the first months, but we are still 0.15, around that. We see for Germany, lead months 1 is a bit of a problem. We have not fully understand why, but you see, in most cases, we are in the positive range. This is already something. To summarize now for Germany, temperature is better than precipitation. I've not shown that our drought indicators, like standardized precipitation, evaporation index, they have more skill than precipitation alone. Yes, first forecasted month works best. That is already something, because it is released the 5th or the 7th of every month, and till end of the month, there's still 3.5 weeks left. This is something. Yeah. The next 6 months perform weaker, but still better than the climatology. And I need to say that is also good news. Extreme months, so very dry, very hot, they can be forecasted better than average conditions. For early warning, this is good news. Yeah, because we want to forecast the extremes to be prepared. Now, let's now look at the big globe. Towards global bias correction for the global CS5 project. Now here we have now precipitation, we have temperature. This is lead month 0, which is the first month. This is the first 3 months, that is the last 3 months. On the left side, you see precipitation. On the right side, you see temperature. Now, and you see, I said 0.3 is, we are very happy with that. We reach here up to 0.25, which is close to 0.3. And you see, for temperature, there is a lot of skill after our correction. I'm not in all regions. Yeah, you see also Southern Africa is a bit of a problem here. Yeah, the very south of Southern Africa. But I mean, along the tropical region, yeah, that looks already promising. With respect to precipitation, when it comes to water, it is even more challenging. But it is there are regions where up to 3 months and even up to 6 months, there is skill. Yeah, there is skill. Lead month 0, which is 1 lead month, this is already also something, but there is skill. And to summarize, yeah, there is forecast skill for precipitation for specific regions, for temperatures, it's for many regions worldwide. And if we look at the globe, then we see this is the Köppen-Geiger climate classification. It's tropical, arid, temperate, cold, polar, and so on. And then we see, you know, for A, that is the tropical regions, that lead months 1 is very nice, but even for further lead months, yeah, we are not around 0.2, but we are around 0.1, which is already something. The tropics perform best. Now, Jan also analyzed 36 extreme droughts worldwide with different SPEIs. You know, we just have a look where these droughts are. He was looking at the 2 most extreme droughts per continent in aggregation period till 24. And then let's have a look what's the outcome. When there's a big drought, you have a big circle. When it's a smaller drought compared to SPEI index, then it's a smaller cycle. But you see, for all of these droughts, we are better than climatology. Yeah, every drought is predicted better than climatology. That is something. Yeah, that is something. Now, let's come again to Africa. In May 2024, there was over wide regions of the African continent have been very dry conditions. This is SPEI1, and the index you see it goes down to -2, sometimes -3. Yeah, there was a big concern about humanitarian catastrophe, and now you may say, okay, let's look at this May 24. And that is now when the forecast beginning of May. This is the forecast of April, the forecast of March, February, January, December, and November. And you see over months in advance, you could see, oh, many parts of the African continent are running in a very dry situation. So successful early warning 7 months before the event. Now, so our issue really is to improve the global seasonal forecasts. That is now in a discussion paper, which is still in discussion, where we put all these data sets here in a discussion paper, and we hope that it is be published soon. Now, let me go now to another region of the world, which is of great importance, and at least we in Europe, we only touch it every now and then. That is the Greater Horn of Africa region. It's the Blue Nile River, which carries most of the water of the Nile River, and it is generated in the highlands of Ethiopia, and then it flows to Sudan, and then even to Egypt in the Mediterranean. And what we want to, let's say, we want to contribute to a better management of this new dam, the Grand Ethiopian Renaissance Dam. Yeah, and that is a hotspot region, just a bit similar to Germany, but from a humanitarian point of view, of course, a catastrophe. There have been extreme rains in 1920, followed by floods. Then there have been 4 consecutive failed rainfall seasons, and after that was a severe flooding again. So it's one catastrophe after the next. Yeah, and that, of course, is difficult because it's a comparatively poor region, and it is even a politically sensitive region. In Sudan, there is a humanitarian catastrophe, and even in Ethiopia, there's a lot of trouble, to say it in a bit neutral words, and it is difficult to do research there. It is very difficult to research there, but there is need. It is need to do research to improve this kind of predictions. So what we do is here, we apply our PyCast system to that region. We do both the statistical correction and the AI-based correction. We work with satellite data. Luckily, because we host students from Sudan and Ethiopia, we have available station data in both countries. And then we do not, in the project, we do not only stop with hydrometeorology. There is hydrological modeling, there is crop yield modeling, but I'm not going into much detail here. And we are not only doing research there, we do a lot of, let's say, scientific exchange. That is what we call co-development approaches. That was our kickoff in Addis Ababa. I used to say this is one of the most difficult workshops I ever organized in my scientific life, because the Sudanese colleagues were not able to travel by plane. Khartoum was closed. They need to come to Ethiopia, to Addis by Port Sudan via land and buses, and due to German travel, let's say, rules from KIT, I was not allowed to reimburse them cash. Yeah, we needed to organize travel in advance, which is not easy anyhow, but we managed, and it was highly appreciated. We also did a WRF hydro, a hydrological modeling workshop in Addis Ababa. We did several courses here on the software tool in Nairobi in 25, even twice. That is how it looks like. Dan Weber, Windman Nakta Savadoro explaining the Python-based code. So a lot of effort is also entering here. That are the participants, particularly in the last course. They are somehow the national representatives of the Outlook Forum. Yeah, they need to decide later on for the different countries from South Sudan, Tanzania, Uganda. They need to, let's say something about the seasonal outlook within their authorities. We have established a community meeting about the software. So Windman Nakta is explaining together with the PhD students, Yasia, Rebecca, and others. And we have 40 registered users, and even now when the project is over, we try to continue this kind of training and yeah, to help people to apply the tool. Now 25, 24, but also now recently in 26, this is still an old picture from 25, we have been invited to present our results to the Greater Horn of Africa Outlook Forum. Our results are only one piece of the puzzle. Yeah, I mean, they have their specific own tools, but one additional piece can be very helpful, and that is our role here, that we put another forecast information in that then can enter the Greater Horn of Africa Outlook Forum. But now just some few words about the AI method. That is what we call AFNOcast, an adapted Fourier neural operator developed by PhD student Rebecca Wiegels. That is now also published in a journal. And that is working completely different to the statistical approach. I'm not going into the details here, but is the AI-based method really doing better or differently than the statistical one? I need to tell you, albeit it always sounds like AI is the solution to everything. Yeah, it is not. For Rebecca, it was not trivial to show that the AI-based forecast is better than the statistical forecast. This is now the continuous rank probability skill, so not the score, but the skill. Still, the lower the number, the better the skill is. You see the big problems of the CS5 raw data, and then you see the statistical approach in here in brown and the AI-based in blue, and you see they're very similar. And you need to go to rather high monthly values that you see slight improvements. Yeah, slight improvements from the AI-based method compared to the statistical one. Yeah, so it is only that there is a slightly outperforming, and that is only for heavy rainfall. When it now comes to the spatial differentiation, yeah, it's getting a bit complex. So you see now, this is the Blue Nile region, this is Ethiopia, this is Sudan, this is the Blue Nile. Here, the Grand Ethiopian Renaissance Dam is placed. And you see, this is now again the skill score, 0.3. We are happy. Lower than 0.3, yes, please, but not negative. You see, the raw CS5 has nearly no skill in the Blue Nile, Upper Blue Nile region. When it comes to BCSD, this is now Liedman 0. Yeah, there is skill, but also in the highlands of Ethiopia, much more skill than here in the lower part of the Blue Nile. When it comes to Liedmans 1 to 3, there is still some skill, more skill here after the dam. And when it comes to the next 3 months, then the skill is going to, significantly down. And now that is interesting. For the AI-based forecast, yeah, we see, yeah, it has skill even after month 4, but mainly actually only in the lower part, yeah, in the Sudanese region. So you see, there is improvement, but it is spatially, let's say, different. It is not that there's improvement always, and there is not that, let's say, one method is always better than the other. So BCSD, the statistical approach, dominates short lead times, and the AFNOCAST is better at long-term horizons, but only in the Sudanese part. Now, again, when we look about the skill improvement of the statistical approach compared to the raw, yeah, because we still need to justify why are not just taking ECMWF seasonal forecast, yeah. Then you see in many parts of the Greater Horn of Africa region, there is improvement. This is just the data, which coming in addition. So it's a skill improvement. But of course, yes, regions remain like here in Somalia, yeah, in Tanzania, where there is no really additional skill improvement. So we need to look very carefully for which region there is skill improvement. Now you say, okay, there's one example now where the Outlook Forum skill that was not really optimally, that is now May 24. That was here the probabilistic forecast from the Outlook Forum. So you see for May 24, they forecasted more below average conditions, but then that is a reference, the observation, it was actually different. It was above average conditions, and here we see our forecast actually would have helped, yeah, to improve this forecast because our corrected forecast was much closer to the reference observation. The 2015 drought, yes, that was a very big one, also due to El Nino conditions. That was what was observed, very dry conditions in many parts of the Greater Horn of Africa region, not here in Somalia, and that was the forecast. But it is not that bad. I mean, this region here, Somalia, was overestimated. The extension was overestimated. But you also see, you know, that small scale features, you know, like this one here, between Kenya and Tanzania, that is captured. Yeah, and that, of course, for decision making is crucial. Now, we have an ongoing PhD, Yasser Mohammed. He is working on extending this forecast also to hydrological modeling, to crop yield modeling. This is now his WRF hydro-based monthly soil moisture. He's comparing it to satellite-derived CCI soil moisture, and that is quite nice agreement, as we see here. At the end, it's all about validation. And now he's also doing, let's say, he's transferring the forecast, that is now temperature and precipitation, into crop yield forecast. That is the El Gedaref region in Sudan. So that is ongoing work. If you're interested further reading, that is one example here, how we do this bias correction very early. Very interesting for you as economic people. For the Upper Adbara Dam in Sudan, we were able to show the economic value of the forecast. We calculated if the dam managers would have taken into account, or will take into account, the seasonal forecast in the operation, how much money they would save. And we came up with a number of 16 million euros a year. So seasonal forecast-based actions achieves potential economic savings up to 70%. Yeah. So if you take the forecast and take early action for the operation of the dam, and for the Sudan Upper Adbera Dam, we know these numbers for electricity, for power generation, then it would be $16 million US. The details you can find here in this publication. We also work with runoff forecasts, ensemble Kaiman filtering. This is an example of Brazil. And when you would like to know more about the limitations of precipitation data in the African continent, in particular here again on the Blue Nile region, the problems of Era 5 land, then I recommend this publication here. Together with another student from Munich, we also contributed on yield forecasts, also for seasonal climate modeling for Argentine and for also region in Europe. So let me come to my summary and conclusions. Again, these seasonal forecasts, they are probabilistic forecasts for every month and for entire seasons, not for individual days. Yeah. So we forecast an months, an anomalous, albeit the forecast itself is day by day, but we need to average over months. Yeah. We are not forecasting White Christmas the 24th of December. Yeah. That is not, there's no performance, but an entire month, that is what I was talking about. And of course, probabilistic forecasts are challenging for decision making. From which probability on a decision maker would go into action? Yeah, is 30% already enough, or does this decision maker want to have 70%? That is not a pure scientific, natural scientific decision anymore. Please remember, whenever you come across with seasonal forecasts of the raw data, be aware. CIS5 and similar also the US American data, they have biases and drifts. Yeah, and that is why our effort is very valuable. And we are not starting from scratch from our work. We take what the big forecasting centers produce, and then we are improving it. Yeah, that is our duty here. Again, the tropical regions, yes, they benefit most from this improvement. Yeah, I would like to mention, I'm really proud to say we really do significant efforts in training and outreach. This is a lot of additional effort, and it is not paid off in an academic CV, but we do so. We go teaching, and we invest sometimes a lot of money to realize and enable this code design. Yes, there is subsequent impact modeling happening. Hydrology, hydropower, of course, are the candidates. Agriculture, yield modeling, and that may make it interesting for you, yeah, as economic people. What does that mean in terms of South African rand or dollar or euro or whatever? Yes, and it allows early action and anticipatory action. And for quite some years now, in the last time also in Belém, I tried to communicate that in bigger groups, in Outlook, in side events at the conference of the parties, the big climate conferences. So together with other people, we organized side events, and that was the one in Belém. Early warning, anticipatory action, and risk insurance, because insurance people have joined too for proactive risk management. Now, due to our global forecast, I hope I'm not showing something, let's say, completely crazy. Now, for your own region, what would be the most recent forecast? That is now the most recent forecast issued by ECMWF, the 5th of July, and now some days later from our group bias corrected. So that is the forecast initiated in June, and this is the first 3 months. And albeit we are approaching El Nino conditions, yeah, seems like there is more still normal to maybe even more wet conditions, but there is a clear indication for landing in the upper 33 hottest months that have been observed with rather high robustness. So you see the dark orange color, which means for these regions here, we more than 70% out of the 51 ensemble members, they indicate that the temperature will be in the upper tercile. Okay, then I thank you for your attention and for the invitation. I send greetings from our campus Alpine. This is where I'm sitting at the moment. So I'm sitting here in that window. Yeah. We are very close, always also with University of Augsburg, with our Center for Climate Resilience, and all these results could not have been obtained and achieved by a big group effort. My special thanks go to Windman Nakta Savadogo, to Jan Weber, to Rebecca Wiegels, to Jassi Hageltum, Christoph Lorenz, and others, Joël Arnaud, and so on. Yeah, and that's it. Thank you, and then I'm looking forward to your questions.
Thank you very much, Harald. This was very, very insightful. And I think the different methodologies you have developed with your team, they are very useful in helping to provide forecasting to some important climate-related events.